let me introduce about myself. So I'm Nilesh Sutar, currently lead robotics engineer at 10x Construction AI. So I have done my master's in aerospace engineering from Indian Institute of Science, Bangalore. I am very passionate about using simulation tools for robotics development. At 10x, we have been working to tightly couple Isaac Sim with our simulation, with our robotics development effort overall. So I personally believe just using VLAs or just using imitation learning data to to train our VLAs and make them we can't get that to the level of human performance is my belief. Whenever you look back and see what has given us superhuman level performance, it has been simulation plus RL. Take example of DeepMind's AlphaFold or AlphaZero. Whatever has gone to a superhuman level has always been it has been simulation plus RL from scratch without any human input. So that has always solved for superhuman level intelligence. I believe that would be the case with even robotics as well. And people have been exploring use of RL on top of VLAs that are trained in simulation to get to that level of accuracy, precision, or the fluidity in motion, basically. So yeah, that's why I was fortunate enough to get started with Isaac Sim. As soon as I stepped out of college, I was working on autonomous lawnmowers, and using that inside Isaac simulation, we were generating synthetic data for training segmentation models to detect basically where we have lawn and where we don't have lawn. So that's how I started my journey with simulations. So here it is, today all the robotic startups need to understand this, simulation is gonna be the core of all the development that takes place, whether it be the CI/CD pipelines that they want to set up for, say, feature testing, learning from simulation, say VLAs, or reinforcement learning, training policies, metric evaluation, edge case formulation, identification, whatever it is. So everything has to be tightly coupled with simulation if you want to develop a robust system, right? So the problem that today that we are going to discuss is texture level synthetic data generation. So why this is critical? Let me explain you. Say there is a, let's discuss the applications directly. The images that I have here, one is the drywall and white compound that you see. Then there is a broom sweeping, that is a cleaning application. Say there is car painting or leaf diseases on a leaf or surface defects in manufacturing industry. These have one thing in common. So here the region of interest is on a particular mesh, right? And the current classical, the current simulations engines say Isaac Sim, they don't give you annotation of this region of interest, that is surface level annotations. So if you look the synthetic data generation workflow in Isaac Sim, all the palette boxes, for example, I have taken this example of palette boxes. ARM is picking up boxes on the palette. So if you see here, each box would be by default segmented as a single label. But this is fine for when you have a pick and place, just picking one box from this place to that place. This is fine. But what if you want to detect if there is a label on the box? This means that you have to have surface level annotation. You have to first detect on what face, on what surface there is a label or not, right? So this is not currently possible in Isaac Sim. I have been following with developers at Isaac Sim Then like currently they don't have any plans to enable this texture level annotation. So we decided to build it kind of like get hacks and build it on top of IsaacSim so that we can extract texture level data. So let me just short info on what are textures. So textures are nothing but different kind of just PNG images that we apply on a mesh. So there is a base, roughness, normal, height map. These are the different kind of images that when you apply on a mesh, the renderer through the material definition library of IsaacSim knows how light reflects from that mesh. So basically, it's a way of defining how light would interact from that mesh. So this is critical because once you are in this image area, it opens up a lot of possibilities that we can discuss later. So what is texture mapping? So you have a 3D model. 3D model is made up of surfaces, small surfaces. What do? You just unwrap the mesh. Once you have the unwrapped mesh here, you then have a texture image, right? For example, we are taking image of our global map. Then what we do? We map this onto our unwrapped mesh. Once you do that, once you feed this to this through the NVIDIA's material definition library, the renderer now, whenever you take a photo of that mesh, it will know which part of the mesh surface maps to which part of the texture. That way, whenever you click a photo in simulation, you will actually get the visual as if the mesh has been painted with that texture, right? Now, how do you go towards semantics, extracting semantic data? So here we have this texture, RGB texture, which is actually, when you take a photo, you'll see that on the mesh. Now on the right hand side, I have manually annotated continents on that global map. Now what I want to do here is whenever I take a photo of that Earth, right, I'll get an image this way. What I want here is that IsaacSim should give me a corresponding semantic map, which should look like this. So remember, our RGB texture is like this, semantic map is this. Now we have taken the photo from this perspective, and I want the corresponding semantic of that particular image. So this is not possible currently with IsaacSim. If you do this now, what you will get is a single color, single labeled image. Say it will just label the entire mesh as a red color, right? So that's not what we want. So how does that, how do we do that? So the answer is like, we have to do ray casting. So the camera has taken an image, which is NVIDIA's internal renderer. The NVIDIA's internal renderer has captured the image. We don't know anything about how it has captured the image. All we have is image with us and the camera intrinsics. Now what we want to do is do inverse, like go from pixel to ray. So from each pixel that we clicked photo from, we want to find which ray in the world, in the camera frame will, like which ray has caused that particular pixel. So that is like we have to do inverse, like inverse intrinsic transformation. So it's pretty like straightforward, not much complicated of math. Basic is just do the inverse of the intrinsic matrix, and you have the UV coordinates on the pixel, and you will get the direction of the ray. Now this is how it will look like. You have the image, and now whenever you have used, you'll get the hit points. Basically, these are the rays that have actually captured the image. Now let me just go into a little more detail about how do we, because see here we have the cross is on the 3D mesh surface. The coordinates are in 3D. For example, it's XYZ. Now we want to go from that XYZ coordinates to where it was mapped on the RGB global map texture, right? So here we have to use barycentric interpolation, which takes our 3D hit points XYZ and we project it onto the UV, like the UV space. UV space is like the image space, row column space. So once we do that, we we go from this 3D hit points to the UV coordinates. Now this is very time taking process if you want to do this on GPU. What you want to do here is use NVIDIA's Warp library. Here, once you have the input rays and the source mesh, you can do this in like sub milliseconds or like 1 or 2 milliseconds. Like for even a 4K image, unlike if you want to run this on CPU, this will take like literally 10 to 15 seconds. So you have to go with like NVIDIA's Warp library so you can run this in real time. So yeah, basically take the rays, take the source mesh, pass it through NVIDIA Warp kernels, and what you get is directly barycentric coordinates out. Right. So now we have the captured image, and then we used our semantic pipeline. We used the reference semantic map. Whatever image was captured and the hit points that we have got from the camera, the corresponding semantics were marked over there. And if you do this, the output that will give is the correct semantic version of the captured image. So that's what was our target, right? So this is our use case, that how we are using. This is our robot in the top. It has a camera. The green rays are like illustration of how we are doing ray tracing from our fisheye camera. We get the RGB image and then we have corresponding semantic map that we get output. So what this has enabled us? First of all, like going out in the field and taking out images of construction sites is very painful. Manually, like collecting data, you can get like maybe 100 or like 50 per day, which is like not at all feasible. To train a semantic model, you need like thousands and thousands of images, which is not like economic. So what this helps is, you get a mesh, you put a texture on it, then you do a semantic, you manually annotate the first semantic map over there. Then you can generate tons of other images from different perspectives, because now you are able to use this texture mapping and manually annotate this, right? So this was not possible earlier. Now, whatever field it might be, because I heard like, say, the presenter for the Boson Motors, they were doing the segmentation models and have collected like 4,000, 5,000 images manually annotated. But if they have done this using, say, this pipeline, they could have scaled this data to, say, like 10x, maybe this 4,600 images. From one shot, you can align the shots with different angles, and you can actually convert this data, like, say, 50,000 images just with this trick. So this applies in all, literally in all domains which are dealing with surface level defects. Maybe it's cleaning industry. For example, say I can relate this to Clutterbot as well. Like they said, texture level information is not available, right? So you can literally enable this texture level information with this hack. You can enable semantics. This even allows you to train your robots directly in sim now, because earlier we can't get this kind of ground truth from the sim, but now we can now have our autonomy stack run with from the ground truth of the sim. Cool. Thank you, guys. Also, we are hiring, and you can scan this link to go to our workable page, and please apply over there.